Okay, so today we're going to study dynamic controllers and filters. Somehow, dynamic controllers, filters, and quite a few other things, such as observers, are similar. They present a class of objects in control which have common properties, and somehow it is good to understand those common properties, the usefulness, etc. So the goal for the lecture is to somehow understand the similarity, commonness, and so on, and see a couple concrete examples of usefulness of such objects. So let us start by getting the terminology. First, let us consider a system, right? You remember, system is a generalization over what we considered as a ODE, or the ordinary differential equation, state space system, like state space plant, transfer function, and so on. System is somehow a general object that can be represented in any of those forms. So a system can be said to be characterized by how it relates its input to its output, right? That's basically what the system is. You have input, you have output, system does something to it, right? Transforms input into output. The way it transforms it is basically the entire characteristic of the system. So for example, a controller can be seen as a system that takes X and returns U, right? Basically just by multiplying X by a matrix. A state space plant can be represented as a system that takes U, it's multiplied by B, and it acts in this ordinary differential equation and returns Y, which is proportional to the state. So again, there is the input U, output Y. Same in Laplace representation. Let's say you have Y as your output, W as your transfer function, U as your input, all in state space, in the form of Laplace images. Then it again is a system that characterizes by how it takes U, mapping it to Y, right? Good. So somehow that's what system does. Now, some systems can be said to be static. They're static because what they do is they just take input and make an output which is proportional to the input, right? So they make output proportional to the input. For example, U is equal to kx. X is just multiplied by matrix. There is nothing here that is going to change. There is no evolution, no development. It is static. Throughout the whole functioning of the system, this relation between X and U is going to be exactly the same. It is given by this matrix K. There is no change detectable within the system. In Laplace domain, we can say that Y equals to 10U is also an example of a static function. It just multiplies this input function in the Laplace domain by 10. Again, there is no change, nothing happens. All right, to understand why we created this term, let's see its antagonist. So the other term that is quite important, and that is dynamic systems. And now we come to the point of this long introduction, right? Dynamic systems. So simply put, we could think of dynamic systems as something where input and output are related not just proportionally, but also through the derivatives. All right? It's not just the input outputs themselves, but the derivatives which relate to each other. So for example, this is a dynamic system. And you remember from the very beginning, we were calling those dynamical systems. So U is not related to X. U is related to X dot as well. So it relates to X and X dot. And Y relating to X is still not proportional to U, right? So while this equation itself is static, the relation between Y and U is not static. It depends on X, right? Depends on X. So to be a little bit more specific, let me dwell on this for a second. Let's say that in the very beginning, X is equal to 0. Then Y would be equal to 0, regardless of what U is equal to. So no matter what U is entering as an input, the output in the very beginning would be 0, because X is 0. Only later, when U had time to influence X dot, and X started to follow the changes in X dot, only then we would find that Y started to somehow resembling X, reveal what U has been like. So you can see that the output here does not only depend on U, somehow depends on what X is at a given time, right? On initial conditions, we can say it depends. But since any state, we can think of it as initial conditions for some future development, it is fair to say that Y depends only on not only on the input, but also on the state of the system. Okay. Exact same situation is here. We don't see the state quite obviously here, but we know that the same is true in this case as well. It is obscured by the fact that in our working with Laplace domain, we always assume 0 initial conditions. So because initial conditions are fixed, somehow this representation suggests exact relation between input and output, right? But that is only a convention that is useful for making mathematics with transfer functions. We know that the underlying system that this describes would have a different initial condition, not necessarily 0 initial conditions. So what I said about the previous example is true here as well. Or here, OD. Here is quite clear. We know that the solution would depend on input, but particular solution depends on input. General solution depends on initial condition, like fundamental solution. So those systems are dynamic. And you can see there is a quite difference between static and dynamic systems. Static systems just multiply something by a number. Dynamic systems behave like differential equations. They have their own state, which can go down, disappear, can go up, they can follow a trajectory and so on. But they quite definitely not proportional. They don't just take input, multiply by number, and give output, right? Okay. So static systems are more like linear algebraic equations, while dynamic systems are like linear ODE, right? Linear ODE. State is a distinguishing quality of dynamic systems. If you have a dynamic system, you have a state. If you have a state, you have a dynamic system. That is a key idea, right? Okay, now that we have this terminology, right, we decided between static and dynamic systems. Let us consider our Leuenberger observer. Our Leuenberger observer is described, like this, right? The input to the Leuenberger observer is Y. The output to the Leuenberger observer is U. Please don't be alarmed that U appears also here. you can always substitute minus kx here, and you would just get a minus kx, a minus bk, right, x hat. So the fact that u appears here is just so we preserve the appearance of Löwenberg observer, but it does not imply anything about its structure being strange or different from normal, right? Okay. So input, output, right? Now, this clearly is a dynamical system. It has a state. The state of the system is x hat, right? X hat. So here's the state. And the output depends on the state. Same as any other dynamical system, the output may follow input. Doesn't have to follow it as in trace exactly, right? It can follow it in a variety of ways. But it would follow the input somehow, especially since it is a stable system. We would design it to be stable. So we don't expect that output would diverge somewhere, right? But it is not static. It is not quite like controller. Now, if we consider it together, like those two things together, notice that this is what we would normally call Löwenberg observer. This is what we would call proportional controller. Now, together, they form a dynamic controller. So it is a dynamic system, but by extension, we can call it a dynamic controller, right? So a dynamic controller, we can think of it as a controller that has its own state, right? So a controller that has its own state. In this case, the state of this controller is x hat. So with that, we can see the difference. Static controller was something like this, right? Something like this. That is a static controller. Or dynamic controller is something like this. Right? Something like what we see on this slide. Yeah? This guy. That is the dynamic controller. So dynamic controller has its own state. Now, in terms of sort of like beautiful images, you can think about it this way. Static controller does not have a memory. It cannot remember anything that was happening before. Dynamic controller has internal states which act as a memory. So it can do things that require knowing what happened in the past. That is a beautiful image. It's not a good mathematical description of anything, but I think, like same as other beautiful images, it helps you remember. So if you want, you can, keep it in the back of your mind, right? Static controller does not remember anything, takes what is in front of it, transforms it linearly. That is all. Dynamic controller takes into account what was happening in the past, storing it in its memory in the form of state, right? The state of the control. Okay, all right. So this is the example of a dynamic controller. Now, dynamic controllers, you can come up with many other versions. Löwenberg observer is just one. We can come up with a general form of a dynamic controller. So a general form looks like this. Derivative of internal state of a dynamic controller. State transition matrix of a dynamic controller. So state matrix. Input matrix of a dynamic controller. Observation matrix of the dynamic controller, or output matrix if you want. And this is what you normally call feed through for the dynamic controller. Why feed through? Because this is what takes input and multiplies it the same way as a static controller would do and pushes it to the output. So it bypasses the state. That's why we call it feed through. All right. If you want to visualize it, you can think of it this way. we have input u, we have output x, oh, output y, sorry, right? And then what we have is a controller here with internal state. So right, dynamic controller here is an internal state. But feed through, what it does, it bypasses this dynamic controller and adds itself to the output, right? So we can think of it as D matrix here, just taking input and putting into the output, right? Of course, in this case, this is input. In case of this guy, that is input. That will be output, right? Okay. So you can see almost everything is the same as for state space system, except input for the controller we denoted as y and output as u. Because controller we expected to produce u, so control, and input to the controller is some kind of signal that comes from the plant, so from the plant y. Okay. So Leuenberger is a particular instance of this dynamic controller, right? Leuenberger, what it does, it has A, which is the same as for the main plant, except not exactly. Like you would think it is the same, but actually A for the Leuenberger is A of the main plant. So let me put it like this. AK for the Leuenberger is A minus BK. That is what A for the Leuenberger is actually. BK for the Leuenberger is actually equal to, let us look, let's find, like what is multiplying the input? Well, actually just this guy, right? And by the way, I forgot to mention when I say AK was A minus BK, it is actually A minus BK minus LC, right? So it's actually minus LC. But BK is just L, right? All right. Let's go to the next slide again. What is CK? Well, it is minus K. Okay, so what is DK? 0. There is no feed through. So you can see that Leuenberger observer is somehow the instance of this general form dynamic controller. Point is that there are many dynamic controllers possible. Now, there are a few interesting theorems about dynamic controllers. For example, there is a proposition that the dimensions of x in the controller do not have to be bigger than the dimension, the state dimensions of the original plant. So we don't have to have more states in the controller than in the plant. For you, if you are like machine learning minded person, you may think of it in terms of like, give it more memory, it would somehow learn, etc. But for control, there is somehow this idea that you don't have to give it more dimensions of space, state space than for the plant. It's not necessary. So it gives you a very good indicator of how to design those controllers, right? On the other hand, you can, looking at this, you can always say, all right, but what if we get rid of all of this and all of this, and we just have u equals to dky, right? What if we just get a static controller that directly gets output of the system mapped to the input? So in a sense, we go back to your something like full state feedback, but now it is not from x to u, it is from y to u. What if we do that? Well, there is another theorem that says that if this guy is not a full state feedback, like if it is not identity or something like identity, so like something invertible, you may not find the controller that would actually be able to. My apologies, I misspoke. If y is not somehow like a one-to-one image of x, where M is invertible matrix, you won't be able to find such decay that would make your system stable. So in a sense, this limits your, imagination in terms of what you can do to less options. Like you know that you need something here. You know that you don't need too many dimensions, as many as x is enough. And you know that limiting yourself to just this type of controllers is not going to always work. So, it's good to know that you have limitations both upwards and backwards. Right? Okay. Last beautiful image for you. Or let me draw it. So if you think of a plant graphically, so imagine this is a plant. I'll put here plant. And the plant has inputs and outputs, right? So here's the input to the plant, which is your control, U. Here's an output to the plant, which is your output Y, right? Then you can also think of a controller as a similar kind of object, right? Here's a controller. It takes as input your Y, right? So Y goes as input. And as output, it gives you your vector U. And here, this plant has the state X. And the controller has state X hat. Is sort of quite beautiful in how symmetric it works. Like both plant and the controller have the same structure, same input-output structure. They even visually look very similar. And this is a general case for linear systems. So it's not like you're considering some one instance of what you could do. You are more or less considering everything that can be done for a state space representation. And you remember, any linear system can be represented as a state space system. You basically are limited to those things, like this dynamic controller. We call it dynamic output controller, actually. That's a full name, dynamic output controller. And it would have the same structure as your object that you're controlling. So there is this beautiful symmetry there. All right, good. Any questions so far? Nope. All right. Then let us look at concrete examples. So Leuenberger was first concrete example. Now next concrete example is PID. PID stands for proportional integral derivative controller. Before in the course, I already talked about proportional derivative controller, PD controller. Now I'm talking about PID. So here is proportional part. That is a scalar case, right? So Kp is proportional to error E. Here's the derivative part. Kd is proportional to the derivative of the error E. Here's the integral part. The output is proportional, Ki, to the integral of the error E. notice that we use this standard trick where we put E of tau by d tau from 0 to t, right? Okay, that's just notational thing, but yeah, this tau here is different from this t only because it's going to be integrated away, and we leave this t here to go back to the time. All right, so this is a proportional integral derivative controller. In vector case, so when we have more than one state, it is quite the same, right? So matrix of coefficients times E, matrix of coefficients times E dot, matrix of coefficients times integral of E. Quite simple, quite simple. Now, this controller specifically is designed mostly for second order systems. The reason it is designed for second order systems is exactly the same as why PD controller is designed for second order systems. Because second order systems, especially mechanical systems, usually the highest derivative, second order derivative, right, would, you can basically write it as second order derivative, y double dot equals to something y dot, something y plus u. And making control first order controller, so with derivatives here, allows you to somehow directly, work in the second order form without even going to state space. That is the idea. That's the idea. In state space representation, obviously, you don't use x dot here, right? That's you're not going to get mathematically meaningful results. So it's for second order systems. All right. Now, this controller is similar to what we studied before, right? So like LQR or pole placement proportional controller. But this part, integral part, it allows us to achieve robustness. Right? And in this particular case, the robustness implies the ability to compensate static additive disturbance. So, for example, you have a robot, and there is a static force that pushes it away from the goal. Like it should be here, but the static force pushes it a little bit away, right? So this type of static force can be combated by this integral part. We'll come back to it after we finish discussing PID. I will discuss this property in just a couple slides. Okay. Now let us consider PID in Laplace space, right? So I, as usual, transfer the output U in the Laplace domain, input E in the Laplace domain. What we have is Kp is proportional to the input, right? Kd is proportional to the derivative of the input. So derivative of E would become SE, right? Now, the last part is proportional to the integral of the input. So the integral of the input would become 1 over S. We didn't, I don't think we studied this, but I think you would probably believe me that if derivative gives you Laplace image of a derivative is, let me put it here, right? Is if dx dt transformed into a Laplace domain gives you S times x of x of s, right? Then integral of x with respect to time int, I would put it just as an integral. If we do Laplace transformation of that, we get 1 over s times x of s. Right? And if you think of integral as antiderivative, then I think it will start making sense. It'll start making sense. All right. Well, of course, we can prove it just by derivation. We get definition of what Laplace transform is. We substitute the integral of x, do some tricks with the integration, we get this result. So it's not like, it's not a mathematical proof. I'm just giving you my intuition. So the integral will become 1 over s proportional by k. So we could write it as u is equal to, and let's be careful here, kd times s squared. So kd times s squared, ys squared, because we're divided by s everything, right? Kp times s, again y times s, because we divide by s everywhere, so we get s here, the s to the denominator. And ki multiplied by nothing, because again we put 1 over s into denominator. And here we have 1 over s. So if we open this fraction, we would get back our kd times s, kp, and ki times divided by s. So that is the transfer function. Let us notice that this transfer function is unusual. The numerator has higher degree than denominator. That's how you know it's not a dynamical system. It is a how should I put it? It is a dynamical system. It's just not a plant. Right? It's not a plant. Plants don't behave this way. Plants don't have numerators with a higher degree than denominators. Yeah. Okay. Now, it would not even be obvious that this controller has a state. It's I have to prove it to you. So let me prove it to you that PID controller has a state. To do this, I would like to rewrite the controller in the state space form. So for that, I would consider e dot as input, we call it y, right? So that is the input to the controller. As a dynamic system, it has input, has output, right? So input would be y, which is equal to e dot. And we define the state of the controller as z equal from 0 to t, integral from 0 to t of e of tau, d tau. Right? So this integral part, we'll call it a state z. Right? Now, what we can say is y, so e dot, is multiplied by identity 0, right? So this whole equation here becomes what becomes e, right? This whole expression here is equal to e. That is equal to z dot, right? So if we differentiate this, we'll get e, right? Derivative of this expression would be e. And indeed, that is what we write here. Okay. E is equal to, here, here. All right. Now, what is the output? Output is PID, proportional integral derivative. So proportional component times E, derivative component times E dot, integral component times Z, so times integral. That's it. So now you can see this is equivalent to PID, but now we can see that there is a state. The state is Z. And indeed, this integral part behaves like a state, right? It the best way you can think of it behaving as a state is by considering the fact that if your controller stops, like your whole system stops, let's say at a certain position, Like you say, your robot is fixed in this position, but you have integral part of your controller running still. And let's say there is an error, like you should be here, but you are here, like there's an error. This integral part will continue to grow because it integrates error, right? So if we go back, the integral part here, it integrates error, right? So if we are stuck like in the wrong position, error is not zero. So it is going to be integrating, and it means that this value here is going to grow. It's going to keep growing. So your output will keep changing. So somehow your output does not just relate to your input statically, like it's not just the input that is transformed linearly to get an output. It depends on how long you have been running with the static error. The longer you run, the bigger your output will be. So if you're stuck here, your output will keep increasing until at some time, you'll start to compensate, and go towards a position where your error is zero. As soon as your error is zero, this will stop changing. This will become static. So that's how visually you can imagine PID having a state. It has a state because it acts like something is a state. There is something that keeps increasing and changing your output because of something internal to the controller. For the same exact input, it keeps producing different outputs. Any questions?
But with this integration thing, there is one problem that if we in the destination point, but we have this integration factor, we won't stop in this destination. We will go forward unless.
That is understood your question, but that is a very common misunderstanding of how PID is supposed to work, right? So it is a misunderstanding, but you're not wrong in terms of engineering practice. So if we're talking about engineering practice, your observation is actually good. So please don't think you made a mistake. Very good observation, but it is still a misconception of how the PID is supposed to work. So PID let me give you a simple example. Okay, let me give you a simple example. So imagine your controller is trying to lift your end effector upwards, but we placed I don't know, something on top of your controller, right? And it made it to lower down, right? So instead of being here, as you expected, after you placed something, it went here, right? That's what happened. Now, it is in static equilibrium here, but your I component, your integration component, is still running. So it's still running, it increases output. It increases.
It's kind of increases the force that is applied to the effector.
Exactly. So as it increases, slowly it starts to combat the gravity and to get it higher and higher and higher. So eventually it gets as high as it has to be. So it is right here, exactly where it's supposed to be without the cap, right? So when we put a cap originally, it went here, then it was working, and it achieved this position here. Now at this new position, error is zero. So your integral component does not do anything now. It just remains, it outputs the same force as before. So, every new second, it outputs exact same force, which is exact force that needed to combat the gravity of the cap, right?
So this integration is kind of auto-tune?
Yeah, it automatically found a force that needed to combat the gravity of the cap. Now, where did your intuition lead you wrong? Now, assume that the cap goes away. Assume I take the cap away. Then this integration component will keep working, and it would, the cup is no longer here, but the force is still applied. So it is going to go way up. And then it will know that there is this gigantic gap, and it will start to compensate backwards, right?
If we have the proportional and derivative error, then we kind of oscillating unless it is equilibrium again.
Yeah. So realistically, you can expect something like this behavior, like few oscillations or no oscillation, depends on if you're overdamped or not. Now, I think the reason for this misconception comes from making this implicit assumption that once you overcome whatever was keeping you from having the static error, once you overcome it, it no longer acts, right? It only acted when you couldn't get to where you wanted to go. And this is not a wrong assumption in general, okay? This is not a wrong assumption in general. For example, static friction. If you have a static friction, you're just stuck here because of static friction. Once you overcome it, it no longer acts. Static friction is not a constant force. Static friction is only a constraint which needs to be overcome. Once you overcome it, it doesn't act. So indeed, integral component would overreact once you overcome static friction. Is it horrible? Hard to say. It depends on the tuning of the controller and so on and so forth. But this is not what I'm discussing here. I'm not discussing static friction. Static friction is not a static additive disturbance. It's not static. Static friction itself is a very strange beast, more similar to a dynamic controller than to a static force. All right, so let's avoid static friction for now. If you're talking about gravity compensation, something like what I discussed, like a cup placed on top of it, or just when you tune the controller, your gravity compensation slightly mistook the weights of the links, then it would work perfectly. Right? However, in engineering practice, there is a lot of small problems associated with using PID. Often those problems arise when you follow trajectories which are very far from your operating point. Like your manipulator is here, your trajectory is way over here. While you're running towards the trajectory, you accumulate a lot of integral component related error. And essentially, as soon as you start to stay on the trajectory, this integral component of your PID feels like it is completely useless. Like you didn't actually need it. You just wanted to arrive to the trajectory and start following it. You didn't have to have this integral component.
So we need to have something like modified PID, where we're using the integral component only for equilibrium case, like point destination.
People do it in all kinds of ways. So typical way people talk about it in research is anti-wind-up techniques. So they imagine this integral part as a wound, like like in the ancient times, people were winding clocks. Like you have a spring, you wind it, and the clock works. So anti-wind-up technique, it's imagining that this PID was wound up while you were going towards the trajectory. And it basically kind of asks PID to forget old part of the integral. It does not integrate the whole integral, only the last few seconds, something like this. All of this is not interesting to our course. It is specific to engineering applications of PID control, and there are many ways to do it, and so on and so forth. So it's something that you'll study in a specific course or during your work with the controller. It's not something that is very difficult to study. There are indeed techniques, and it is very likely you would use some of them. There are alternatives, right? You don't have to use your PID to follow a trajectory which is far away. You can instead build a new trajectory from where you are currently and follow it, right? That would solve the problem exactly the same. There are many approaches. So same as almost anything else we discussed in this course, there are hundreds of things in details and so on that you can dive very deeply. All right. But it is indeed important to understand how the thing works, is like supposed to work in in the conditions for which it is defined. So for PID, in the conditions for which it is defined, so with static additive disturbance, it indeed works. It works perfectly. It arrives exactly where you want it to arrive, and so on and so forth. And in all those examples which I discussed, trajectory following, for example, it will work also perfectly, except there are things that practice brings into the problem which do not agree with the assumption. The system is not exactly linear. Something else happens, etc., etc. And you no longer can discuss static additive disturbances. Yeah, if it is not this task that you're trying to solve, you don't have guarantees which theory brings to you. So it is important to understand, to do practical work, it's important to understand what the theory promised and what was the conditions. If you understand those, you can see where your practical problem breaks the conditions. And then you can study exactly where the issue arises, right? So that's like what I would recommend to you as a practitioner. Don't just go into literature that tells you where the problem with PID is and so on and so forth. Try to initially understand why your problem has issues, right? What assumptions did you break? Why did you use PID? What the promise of PID was? Same with anything, with Leuenberger observer, with LQR controller, with pole placement. All of them have the same similar issues. None of them are perfect for everything. You have to understand which assumption you broke, which premises you had when you used them. And from this on, you start to look into what literature suggests as a solution, as alternative, and so on and so forth. This gives you like systematic understanding of the problem, systematic understanding of what people were trying to do, and you make a rational decision, right? Well, that's the proposition. Any questions more about PID? We have time today, I think. I believe we have time today. So, you can ask.
No more.
Anyone else? Okay, all right. Then I'll go to the next. I'll go to the next slide. All right, now let's discuss static disturbances. Static disturbances is what we promised PID can work with. I explained with this example with the cup how it works, but let us understand it mathematically. I'll give you one of possible ways to understand it mathematically. There are many. So consider a system with a static disturbance D. So D here is a static disturbance, right? Let us say that we use static controller, right? Stabilizing control minus kx. And, we have this closed loop system. So once we put instead of u minus kx, we get a minus bk as usual, but plus d this time. A minus bk would be a stable matrix because it is a stabilizing control, right? Hurwitz matrix. And it means that x would dwindle. But what it would dwindle to? Well, in fact, what's going to happen is it's going to approach a steady state solution. Steady state implies that x dot is equal to 0. Once we put it to 0, we have this equation, right? Here I use x sub s to imply that this is a steady state. So from this, we can easily solve for x steady state. So we put d to the right-hand side with a minus sign. And we invert this matrix to get x steady state is equal to a minus bk inverse times d with a minus sign. So this is your error. If you wanted to go to 0, instead of 0, you are going to this matrix here. Obviously, the error would depend somehow on the eigenvalues of the closed loop matrix, you can imagine, or single values or whatever. So if you have very large real eigenvalues, you can expect that your final error would be hopefully quite small, right? Because this inverse sign would turn a big number into a very small number during inversion. So you'll get relatively small errors. But if they're not very big, then you'll get quite big errors, proportional to D. Okay, we can do the same analysis in state space. Sorry, in transfer functions representation. So we rewrite the same system as S times X equal to AX plus BU plus D. All of those like Laplace representations. Control law is U equals to minus KX. Now I substitute the control law into here and get X out of the bracket. So I get A minus BK times X here. I put it all to the left-hand side, so with a minus sign. And on the right-hand side, I only have D. Now what I have is X can be put out of the brackets. In the brackets, what we'll have is identity times S, right? So identity times S minus A minus BK. So this guy. And I can invert it, right? Multiply both sides by inverse of this matrix. So we get S, X equals to I times S times identity minus A minus BK, everything inverted, times D. That is a transfer function. It's a transfer function between the disturbance and the state of the system, right? That's a transfer function of those. Now, what is the static gain, static steady state gain, right? Well, the way we do it is we cancel everything that has S, right? You know, to compute steady state gain, we take the transfer function, we get rid of everything that has S in it. Now let us remember that this is a transfer function. All of this is a transfer function. We cancel the part with S for this part. And we get everything else, everything that remains. So minus A minus BK inverted. Exact same gain as before, right? That is what's going to multiply our input to get the output. Right, so you can see how it can be done in both state space and Laplace representation. Now we're going to use it to work with integral compensator. So if we knew D, we could compensate very easily by using control law, which would have minus kx minus b pseudo-inverse D. If D lies in the range of control matrix B, then this would just cancel, like after multiply by like D minus B times B pseudo-inverse times D would be 0 if D lies in the range of matrix B. So we could just cancel it this way. But the whole point of disturbances, we don't know them. If we knew, we would do that. But we don't know them. Like someone put a piece of paper or whatever on your robot, it disturbs it, right? Your wires are a little bit more heavy than you expected. There's a disturbance. your payload is a little bit bigger than expected disturbance, right? All kinds of disturbances are possible. So, and we don't know them. That's the whole point. Now we can use integral component in the control law to compensate. So integral component would look like this: minus ki integral from 0 to t of x d tau. So you can see now I keep it in the state space for, why not? We could do all of this in second order systems, ODE second order systems, but somehow this is, I think, is interesting as well. The idea would be, roughly speaking, the same in all cases. Let us present everything again in Laplace domain. So we have S times X equals to AX plus BU plus D. And U would be equal to minus KP X, right? So this guy. Minus 1 over S KIX, this guy. So that is what we have in Laplace domain. Next, what we do is we take this equation and this equation here, right? Those are the same equations as before. And we can transform it into a transfer function representation. So first we take this, substitute here to get this, right? And this, substitute here to get this. Right? So we just substitute the control law into U instead of U. That's how we get equation 17. Next, we multiply everything by C to get rid of this guy. So we get S, sorry, by S. So we get S squared here times AS times S times B KPX minus, right? Minus here we get nothing because this is, cancelled, S over S. And finally, plus D times S here. Okay. Now, next step, we combine everything in front of X. So it'll be, let me put it like this. S squared minus SA minus S, sorry, plus SBKP plus BKI. All of this is going to be on the left-hand side, right? So S squared minus A minus BKPS plus BKI, right? All of this. And we multiply it by its inverse, both sides. So we get the expression 19. And this S is going here. All right. Now, time to analyze. What we are going to do is compute static state gain, right? Steady state gain. So first of all, everything that contains S goes towards 0, right? So this goes towards 0, clearly. This goes towards 0, right? But there is also this guy. So after we cancel all of those terms, we have S divided by BK, and S itself is going towards A. So the whole thing goes towards A. Right? Everything goes towards 0. And that is the whole point of this control. No, it doesn't have a static, its steady state gain is 0. Right? So that's the idea. That's how you can see it as going to 0. Of course, all of this discussion assumes that the closed loop system is stable. So you have to show that this guy here, that's a closed loop system, that this is stable. That I did not show. It's not enough to just slap Intego controller on top of your robot and hope that it is stable. You have to make sure that it is stable. Otherwise, it's not going to converge to anything. So stability is still an issue. But you can solve the stability here in any way you prefer. You just have to put it in a state space form or in the form where you can do pole placement, whichever you like. And that would work. But yeah, if your system is stable, then this analysis shows that your static gain would be 0. Right. Do you have any questions? All right. So far, what we have studied was basically two types of controllers, right? Leuenberger from the last lecture, which we showed is a dynamic controller. And what it gives you is the ability to work with systems that do not have access to the full state information. So you somehow estimate your state, and you can still control it using linear feedback, right? Dynamic controller. Another one is PID, which allows you to compensate for disturbances in your static disturbances in your model. Again, very good. Now, the last example is going to be filters. The idea of a filter is somehow like intuitively is that you have your good component of input and you have a bad component of your input. You want to filter out the bad component, keep the good component. That is kind of like the intuitive idea of filter. So let's consider the problem that goes like this. We have a system, very simple system in this case. X dot equals to AX plus BU, right? Very simple system. Now, let's say that its output is calculated as proportional to the state plus some noise. In this case, the noise is just a high frequency sinusoid. So sine D times omega t, where so WT, where W is very high, a very big number. All right. So we have this kind of thing. Now, what we can do is we can try to filter out this high frequency noise by passing the measurement through a filter that attenuates the high frequency component. You remember our discussion with Bode plots, where we said that your system has a amplitude response. Like there's a specific amplitude of the output frequency, output harmonic, which depends on the frequency of the input harmonic. Any system has this characteristic. So we would pick a filter that has a characteristic of attenuating, so minimizing the high frequency components while being quite benign to low frequency components. We would assume that our X behaves as a low frequency component. It doesn't oscillate very much, right? It is a first order system after all. We expect a epsilon to be like, behave quite like a decaying exponential. So if A is negative. So our low pass filter, how would we describe it? Well, I propose the following low pass filter, where we take it as Z dot equals to minus Z plus Y. Right? And then the controller would be linear controller, U equals to KZ. Right? All right. Let's study how it works. So this low-pass filter, we can represent it in a Laplace form. There'll be C times Z, S times Z equals to minus Z plus Y, right? Which we can, as usual, collect everything on the left-hand side. It will be C plus 1 times Z equals to Y, right? You understand where how it goes, right? We put this on the left-hand side, and then we get C Z plus Z equals to Y, and I get Z out of the brackets. Right. And then we get a transfer function that is written here. We divide everything by C plus S plus 1. S plus 1. So Z of S is equal to 1 over S plus 1 times Y of S. All right, good. That's the transfer function. But you remember the frequency response to this transfer function. We can find it by substituting omega here instead of S, and then finding its amplitude of the transfer function, right? Substitute omega J, and we get the amplitude response of the transfer function by finding its magnitude of this expression. So I did all of this, and I give you this, final answer. This is the magnitude amplitude response of this transfer function. It is 1 over square root of omega squared plus 1. Now you can notice what's going to happen. Your signal, input signal, which has high frequency component, the high frequency component is going to be attenuated this many times. If the frequency is very high, this number is going to be very low. So if we're taking hundreds here, it's going to be divided by 1 over 100. If it is tens of thousands, it's going to be tens of thousands smaller. On the other hand, if the frequency is close to 0, then the attenuation will be close to 1. So it will pass right through without any change. And this way, you can get your signal free of this high frequency component. And this is another use for a dynamic system. Now notice this, what we did here is we just introduced another dynamic output controller, right? Here's the state of the controller. Here's the input to the controller. Here's the output to the controller. But now it is filtered, and now it gets rid of unwanted frequencies. There are many filters that we could imagine. There will be filter with particular bandwidth, so it would get rid of both low frequency components, such as static errors, and high frequency components, such as noise, and can only work in a band. Those are more popular in radio transmitters and so on, where you know the frequencies with which you want to operate. But there could be varieties of uses. Like low pass filter is quite clearly useful thing, because extremely high frequencies are very rare in control applications. Like you don't ask your robot to change its position with a frequency of 10 hertz. So you can imagine anything that has a frequency of 10 kilohertz. So anything that operates at a frequency of 10 kilohertz is likely noise. You can filter it out. And notice that this behavior of being able to filter something out kind of is similar to any behavior of a system with a state, right? You remember when we were discussing earlier, I was saying if you start pushing on the system, and this was in the very first slide here. I think it was right here, right? If you start pushing on the system on U, but your X initially is 0, you're not going to get any output. Your output is going to be 0. It's only when you push for a while that the system picks up through this derivative and it starts to respond to your push, right? It's not going to, so if you started to push backwards, like millisecond later, there would be still no time for X to react. So you would still have no output. You can imagine if you have a heavy car, you can push on it very, with enough force, of course, to overtake static friction, but steadily. And eventually it will go faster and faster and faster. But if you push and pull, so you try to shake it, the car will be motionless. Trying to shake a heavy body is very hard. The heavier the body is, the harder it is to shake it. Something very light, like a pencil, you can shake quite easily. Something quite heavy, like a bucket of water, you can shake, but you have to choose a frequency which is lower, something like closer to natural frequency of the water, of the bucket, right? Something very heavy, the natural frequency will be extremely low. And this is the characteristic of mechanical systems, the characteristic of systems with inertia. And when we do low pass filter, we imitate this behavior. And you can see that a lot of those things that we discussed today, they kind of come to this. Like we have systems with certain types of behavior, which is possible to achieve because of the internal state, right? This low pass filter behavior. Somehow we managed to achieve this observation behavior with Leuenberger observer. Somehow we're able to achieve this compensatory behavior with PID. That is why it is important to consider dynamic filters as a series of options when you work with control. Because you can see this range of behaviors is quite good. And the mathematics behind them is quite simple and natural. So you can still work with them without developing a completely different theory for your ad hoc solution that you have for a particular problem. If you can use a dynamic filter, you will at least have a theoretical background for it. And often a lot of ad hoc solutions come down to a more complicated forms of a dynamic controller. So I guess that is the final, observation for the day. As usual, slides are here. Right, I will stop the lecture and we can discuss if you have any questions.